Everyone, it seems, has their own favourite panacea for climate change. Mine is aliens. But for an increasing number of people, it's geothermal energy. And that's for good reasons. We sit on a big hot bowl of molten rock, and it seems like the obvious thing to do. But in contrast to nuclear fusion, where every small step gets huge press attention, no one ever talks about what's going on with geothermal energy. No one besides me, of course, because in the past months, a few very interesting things have happened. Let's have a look. The amount of energy that resides in Earth's crust in the form of heat is staggering. Geoscientists estimate that the total energy reserves in the upper 10 kilometers of Earth's crust are enough to cover the world's energy needs for several 100 million years. The major problem with geothermal energy is that drilling is really expensive, and the deeper you want to drill, the more expensive it gets. That's why, at the moment, geothermal energy is commercially viable only in places where the heat isn't too far deep down. Then again, the technology of geothermal energy has never been much developed, because if you're drilling already, you might as well drill for oil or gas and use that to generate energy. Oil and gas has become somewhat unpopular recently, and now the technology of geothermal energy production is receiving a close look. And there's been so little done that easy gains can still be made. The first progress report comes from the American company Quaise Energy. It's a spin-out from MIT. They just added another $21 million in funding for their microwave drilling system and say that they want to begin in the fall to test it at a geothermal site in Marble Falls, Texas. Their aim is to drill really deep to places where it's so hot that water becomes supercritical. At supercritical temperatures, water can transport much more energy, and that makes power plants much more efficient. They want to get to such depth by combining a traditional rotary drill with a millimeter wave laser. They claim that this way they'll be able to drill 20 kilometers deep in just 100 days, and that with their technology they could reach supercritical temperatures at 90% of locations across the globe. If that was right, it'd basically solve our energy problems. I strongly doubt that this is going to work, seeing that so far supercritical wells all either collapsed or blew up. Then again, it's not any crazier than what fusion startups promise, and certainly way deeper. The United States has a lot of potential for geothermal energy, especially in the West, so it's maybe not so surprising that our second news also comes from the USA. Earlier this year, the American Department of Energy, DOE for short, selected 2 pilot projects to test what is called an enhanced geothermal system. Usually, geothermal energy systems rely on naturally occurring hot water reservoirs. The issue is that these don't occur all that frequently. The idea of enhanced systems is to drill into hot rocks, push in water, let it warm up, and extract it elsewhere. This could vastly increase the number of potential sites for geothermal energy, which is what makes this idea so promising. One of the projects that the DOE is financing is led by Fervo Energy and will be situated in Utah, where they already have a test site for enhanced geothermal. The test site exceeded expectations in drilling rates and cost less money than projected, which is really quite something. The new project now wants to build on the knowledge that they gathered. The second project the DOE is financing comes from a fossil fuel company, namely Chevron. They have announced that they want to build a small test plant in Northern California. On the opposite end of things is a plant so modest it makes you wonder why it hasn't been done a century ago. It comes from the Canadian startup Eva. Their innovation is that the water in their geothermal plants goes around in a closed loop. The company claims that their system is so efficient that it can generate gigawatts anywhere in the world. They previously had a test site in Alberta in Canada and are now beginning construction of their first commercial-scale plant near Munich in Germany. You might think that closed-loop systems are not exactly groundbreaking new tech, and that's right, but conventional geothermal power plants are open-loop systems. They use naturally occurring reservoirs of hot water or steam. So you see, there are easy gains to be made because this technology has been so underexplored. In my mind, geothermal is the dark horse of the race to clean energy. Yes, at the moment solar and wind are leading, but geothermal might catch up and leave everyone in the dust. And who knows, maybe we even get a few extra volcanoes. I don't often read comments, but when I do, I'm always surprised by what I can learn about myself. I recently found out, for example, that I have fallen for the climate hoax and I'm an anti-scientific climate denier. That's social media in a nutshell. I think a lot of people have a problem understanding me because they expect me to have an agenda. And if they can't figure out what agenda I have, they make one up. But the only agenda I have is that I want you to be well informed. And I'm pretty fed up with climate scientists who insist on overly optimistic messages about what we can achieve and with those who claim the world will end. It's time to get real about climate change. And the reality is that the Paris goals are long out of the window. At this point, limiting global warming to 1.5 degrees above pre-industrial levels is for all practical purposes impossible. Realistically, you can also forget about 2 degrees. Indeed, I think the Paris goals were never realistic in the first place. So what can we expect realistically? According to a recent survey by The Guardian, most climate scientists agree that the 2 degrees target is by now unreachable. Most of them think the realistic expectation is somewhat below 3 degrees. I don't think this is realistic either. Have a look at this infographic from the website Climate Action Tracker. This shows the path that we are on, going by the average expected temperature increase and by current policies. If all the current policies worldwide would be fulfilled according to plan, we might just about stay below 3 degrees. Maybe you don't trust this source, but the assessment from the IMF looks pretty much the same. Current policies put us somewhere at the 3 degrees warming path. This is also what the majority of scientists in the Guardian poll said. But is that likely to happen? Let's look at some examples and compare plans with reality. This is the European Union. This is the target for carbon dioxide emissions. This is the path we're currently on. This is Canada. This is their net zero goal. This is the path they're on. This is the United States. This is the plan. This is the path they're on. So what does it look like? Are we going to live up to the promises that governments have made and stay below 3 degrees warming? I don't think so. I've said this before, but just in case you haven't watched all of my 800 or so videos, the 3-degree estimate is just the average of the model projections. It's not like we know that this is what's going to happen. It could be less than this, but it could also be more. I suspect the reason some people call me a climate denier is that when I say this is likely going to happen, they think I'm saying that I want this to happen. No, these are 2 different things. Let's take the example of carbon dioxide removal. Fact is, all current plans for net zero by 2050 require carbon dioxide removal. The IPCC says so, the International Energy Agency says so, the US National Academy of Science says so, independent reports that have looked at it say so. The plans for carbon dioxide removal are completely unrealistic. We have a tiny fraction of what the plans require, and it's never going to happen that quickly at that scale. Realistically, we'll pretend to do some carbon dioxide removal and fall way short of the goals. Does this mean I think carbon dioxide removal is a good idea or that it shouldn't be done at all? Certainly not. I just think that realistically it won't work. It's a similar problem with our glorious transition to electrified transportation. The International Energy Agency has said very clearly that the necessary grid investments are a critical hurdle in the adoption of clean energies. To meet the goals, most countries would have to put a lot of money into grid upgrades and get it done very quickly. Realistically, in most places, it's not going to happen as quickly as would be necessary. Does this mean I think we shouldn't do it? Certainly not. I just think that realistically it won't work. Or take the so-called hydrogen economy that some countries, including Germany, have heavily banked on. The idea is that we'll store renewable energy in hydrogen, which we can then use whenever we need it. Nice idea. But where do we get this hydrogen from? Here are the plans for such hydrogen from renewable energy projects versus reality. The plans for 2030 are in light pink. Reality is the black dots. The dots are kind of hard to see because they're so small. To give you some numbers, the European target for 2030 is 120 gigawatts in installed capacity. Operational at the moment are 0.2 gigawatts. Do you think the plans for a hydrogen economy are realistic? I don't think so. Does this mean I'm against hydrogen? Certainly not. I just think that realistically it won't work. For me, the relevant question is this. Why do we have so many bullshit plans? I think it's because the people who make these plans don't take the situation seriously. If you're in a serious situation, you give clear and simple orders. Do this now. You don't fuck around and waste time on 20 different things that, hey, would be pretty cool if they worked, but probably won't. If I was in charge of the world, I think I would step down. Some people dream of meeting Albert Einstein. I wonder what Einstein might have been dreaming of. He famously said that God does not roll dice to express his dislike of anything related to quantum physics. And this makes me suspect that one of his nightmares must have been that his theory of gravity would also be turned into a quantum theory. This nightmare seems to be inching closer and closer, but not in the way that Einstein might have thought. Einstein was very much a theoretical physicist, but after trying their hands at developing a theory of quantum gravity and failing, physicists are now trying to measure the effects of such a theory. There are several proposals for experiments around now, and just last week we had a strong newcomer. Let's have a look. As a student, I was fascinated by this problem that even Einstein couldn't solve. How do we make gravity compatible with quantum physics? The problem isn't all that hard to understand. You see, a quantum particle can be in two places at once. It's not like the particle splits and half of it is in one place and the other half elsewhere. The particle is both entirely in one place and in another at the same time. But what happens with its gravitational pull? You'd think that this has to go to both places at the same time too. But in Einstein's theory of gravity, this can't happen because it doesn't have quantum properties. So what gives? For a long time, physicists thought that quantizing gravity was a question of mathematics, not experiment. They thought that if they could just figure out how, they could deduce the right solution. But it's become increasingly clear that this just doesn't work. With that, focus has shifted to experiment, which I think is a very good development. The ideas to experimentally test quantum gravity can roughly be classified into two categories. In one category are those which want to look at the situation when gravity is strong. But for this you need to be inside a black hole or at the Big Bang, or you need to have a collider the size of the Milky Way. It's very difficult. When gravity is weak, it's much easier to measure its quantum effects. Still not easy, but easier because you can actually create these cases in the laboratory. But then you have to find a way to tell apart the case when gravity is quantum in nature and when it's not, and then you need to be able to measure it precisely enough. Previously, we had two different proposals for how to do this, and now we have a third. The first one is to use what's called an entanglement witness. The idea is to take two masses that interact only gravitationally. Then you show that they have become entangled. Entanglement can only be created by an interaction that itself has quantum properties, so this would show that gravity must also have quantum properties. The problem I see with this idea is that it'll be basically be impossible to prove the entanglement wasn't caused by anything else. There are several groups working on this now nevertheless, for example at the University of Warwick and at the University of Groningen in the Netherlands. The second idea is to directly measure the effects of the gravitational pull on a test mass and see how large the uncertainty is. Suppose you have a quantum particle that flies left to right. As it flies, it spreads out because that's what quantum particles do. Now suppose you have another object that is in two places at once and much more massive. So it'll gravitationally attract the first, but how it does so depends on whether gravity has quantum properties. If the gravitational pull does not have quantum properties and is instead smeared out over these two places, then that has the same effect as if half of the mass was here and the other half there. This will cause some spread of the particle that passes by, but if the gravitational pull goes to two places at once, each with the full mass of the object, that'll spread the particle's directions even further. To measure this, you want to take an object that's as heavy as possible and bring it into a quantum superposition. There are people working on this now, for example in Vienna. The new paper now comes up with a third idea that I hadn't heard previously. It's to measure what quantum systems do when you don't look at them. Concretely, they use two masses connected by a rod and suspended from a wire. This is known as a torsion pendulum. They're commonly used to measure small gravitational attractions because, say you put a mass nearby this thing, then the pendulum will turn and you can measure this from the twist of the wire, which is very practical. They now say we set up those masses so that two of the pendula couple together. But this is quantum physics, so nothing ever sits entirely still. Everything always wiggles a bit. And the question is how the wiggling of each pendulum affects the wiggling of the other one. So you set up the pendula, wait for a bit and let them wiggle and interact, measure what they're doing, and then you repeat this a billion times. In the paper, they've calculated that if gravity itself has quantum properties, then there are many more possible outcomes than if gravity is not quantum. Basically, more things can happen. This is a very promising approach because it's easier than measuring entanglement, and one doesn't need to bring the objects in strongly delocalized states. What could all of this be good for? Is it just putting the finishing touches on Einstein's masterwork? I think it's much more than this. Solving this problem will quite possibly also help solve other problems, like the nature of dark energy or dark matter, or what's going on in a measurement in quantum mechanics. So stay tuned. And one thing. My agency says that few of you have turned on notifications for this channel, and I'm supposed to tell you to do it. So please turn on notifications, because otherwise they'll make me repeat this. When I grew up, pretty much everyone I knew had blue eyes, so I assumed most people have blue eyes. Mathematicians call this sampling bias. Now consider that astrophysicists assume that the universe is like what we see around us everywhere. What if that's just as wrong as me thinking the entire world is blue-eyed? The idea that the universe is really not the same everywhere has been flying under the radar for half a century or so. But a new paper now looked at this idea from a fresh perspective and found that it could explain both dark matter and some unusual gravitational waves. Let's have a look. According to this idea, the universe is divided into cells with a structure much like foam, made up of many small areas and divided by thin walls. But since this is physics and not biology, the cells of the universe aren't called cells, they're called domains, and the walls between them are not cell walls, but domain walls. The easiest way to understand the idea is to think of a magnetic material. In a magnetic material, you have atoms that act like small magnets. magnets. They want to align with their neighbors. The warmer the material, the more thermal motion shakes the atoms around, and the fewer of them are aligned. But if the material cools down, you get larger and larger regions in which the atomic magnets all point into the same direction. These are called magnetic domains. In the universe, you don't create domains from magnets, you create them from the properties of a field called the axion field. The axion field has a particle associated with it, the axion, that has become quite popular as a dark matter candidate, but this is not what we'll talk about today. Instead, we'll just look at the axion field. This field would have been around in the early universe at high temperatures, and the idea is that when it cools, it doesn't do so smoothly, but it creates separate domains, the cells of the universe. These cells only differ by the type of vacuum inside of them. They're indistinguishable from the inside. It's kind of like when you're at Starbucks, then you can't tell what country you're in. But most of us do notice if we walk into a wall, and it's the same with the domain walls in the universe. You could measure that we're passing through those walls. This could happen because the Milky Way doesn't sit still. It's moving towards a place called the Great Attractor, where there doesn't seem to be anything in particular, though I suspect it's Pringles. Pringles or not, if we were to cross these domain walls, that'd make magnets all over the world slightly wiggle. However, this would be an extremely rare occurrence, and it's very unlikely we'd notice, so no one's really looking for it. The idea that the universe has these domains generally hasn't been pursued much because it leads to a problem. These domain walls carry a lot of energy, and their contribution to the entire matter-energy budget of the universe increases in relevance as the universe grows. At some point, it would become measurable, so you'll have to tweak the model so that we can't measure it, or that it agrees with the effect that we assign to dark energy. The model adjustments are not super appealing. A new idea is that these domain walls were produced in the early universe, but they collapsed long before the first stars formed. This is what they look at in the new paper. They want to know what the consequences would have been. It turns out to be more interesting than you'd think. They say that the collapsing domain walls would leave behind a lot of small black holes that could be candidates for dark matter. These black holes would have a typical mass in the range of small asteroids or so, something like a few trillion tons. This is a mass range where they're very difficult to detect because black holes with that mass would have a radius of barely a nanometer, so we wouldn't have seen them. The idea that dark matter is made of black holes is generally difficult to make sense of because you'd need the black holes to be produced in a mass range where we wouldn't yet have noticed them, for example by gravitational lensing. The domain wall decay seems to do exactly that, explaining why the black holes are in the range where we wouldn't yet have measured them. They also say that sometimes the domain wall collapse would produce a baby universe instead of a black hole. Physics is wild, man. The domain wall collapse would also produce a lot of gravitational waves with huge wavelengths. The interesting thing is now that there is a collaboration trying to measure exactly this. You see, the wavelength of gravitational waves depend on the size of the system they come from. Stellar mass black holes have sizes of some kilometers, and the wavelengths emitted from them are in the kilometer range as well. This is why gravitational wave interferometers on Earth have arms in the range of several kilometers. But for domain wall collapse, we're talking of much larger distances, light years and up, trillions of kilometers. The only way we currently know for measuring them are pulsar timing arrays. For this method, one uses the timing of pulsars that are neutron stars which emit particle beams. They rotate, and so this particle beam reaches us with an extremely reliable period. If you measure distortions in the pulsar signals from different directions, that can tell you whether gravitational waves stretch the space in between. And just last year, a group of physicists said they have very tentative evidence that they've measured gravitational waves with wavelengths that fit to the idea that they came from domain wall decays. I find this a very interesting idea, though I have to say that they had to make quite some assumptions to make the size of the black holes come out in the right range and the gravitational waves to come out with the right amplitude. So basically, I find it a little too much to swallow. Then again, I don't like any of the other explanations for dark matter or dark energy either, and this one isn't any worse. Thanks for watching. See you tomorrow.